Look at a map of the world, and one geographic detail stands out immediately. At the edge of Europe, Spain lies just across the Strait of Gibraltar from Morocco. At its narrowest point, the strait is only about 14 kilometers wide. A high-speed train could cross that distance in only a few minutes. And yet, in all of human history, no one has ever built a bridge across it. Europe and Africa remain physically cut off from one another. Why have engineers repeatedly failed to connect them here? In this video, we'll look at the strait's powerful currents. Examine one man's extraordinary plan to drain an entire sea, and uncover the real challenges standing in the way of every proposal. During geotechnical surveys in the early 1990s, research teams working in the Strait of Gibraltar encountered serious difficulties keeping their vessels in position while drilling boreholes to sample the seabed for potential bridge foundations. Strong currents and shifting conditions made it extremely hard to hold a fixed position. And several survey attempts had to be cut short. Local sailors sometimes spoke of the strait as an unpredictable, almost supernatural place. The real explanation is more interesting than any legend. Scientists have found that the Strait of Gibraltar hosts a complex two-layer current system. Warmer, saltier Mediterranean water flows outward toward the Atlantic beneath the surface, while cooler, less salty Atlantic water flows inward toward the Mediterranean above it. Where these layers interact, they generate significant turbulence, and combined with storm winds that can reach speeds of over 100 km/h at times, holding a ship steady in the strait is a serious challenge. If the water couldn't be tamed, perhaps one architect reasoned it could simply be removed. In the 1920s, as Europe worked to rebuild after a devastating war, German architect Hermann Sergel proposed a plan that shocked the world: Atlantropa. His idea was to dam the Strait of Gibraltar and lower the Mediterranean Sea by roughly 200 meters, exposing new land and physically linking Europe and Africa. The plan involved a system of large dams across the Mediterranean basin, along with a system of shipping locks, conceptually similar to the ones used on the Panama Canal, to move ships between the new sea level and the ocean beyond. The project was ultimately abandoned. Critics and scientists at the time argued that draining the Mediterranean would devastate coastal ecosystems and that the construction costs would be enormous concerns, serious enough on their own to sink the plan, without needing exaggerated claims about global flooding. Atlantropa faded into the archives, but the dream of linking the continents didn't disappear. By the late 1990s, American architect Eugene Suey proposed a very different concept, a structure that would combine a floating bridge with a submerged tunnel section, allowing ships to pass overhead, while the crossing itself stayed relatively close to the surface, not plunging kilometers into the deep, but remaining within roughly 30 to 100 meters of it. Submerged floating tunnels of this kind have been studied by engineers for decades. Though none has ever actually been built, the technology remains largely theoretical. Suey's proposal faced two major obstacles: extremely high projected costs, and as later seafloor surveys would reveal a physical environment far more hostile than early planners expected. By the early 2000s, engineers with experience from major infrastructure projects, including professionals who had worked on the Channel Tunnel connecting Britain and France beneath roughly 50 kilometers of seabed, turned their attention to Gibraltar. Compared to that project, a 14-kilometer crossing initially seemed straightforward, but sonar surveys of the strait's narrowest point revealed a far more dramatic seafloor than expected. A deep underwater trench rather than a flat plain, reaching depths of around 900 meters at points along that route, compared to just 76 meters in the English Channel. A conventional suspension bridge here would require support pillars taller than several Eiffel Towers stacked together, an enormously difficult structure to stabilize against strong, shifting currents. A deep tunnel wasn't a simple fix either. At depths approaching 900 meters, water pressure is extreme, and the seabed along this route is made of very hard rock, making deep drilling both slow and difficult. But depth and hard rock were, in principle, solvable engineering problems. The bigger obstacle lay deeper still. The strait sits directly on an active tectonic boundary. In 2004, the Moroccan city of Al Hoceima was struck by a powerful earthquake, magnitude 6.4, one of the most damaging in the region's recent history. Earthquakes like these are a reminder that the Strait of Gibraltar sits on the boundary between the African and Eurasian tectonic plates. The African plate is slowly moving north, a process that, over millions of years, helped push up the Alps, and one that continues to build up stress along this fault line today. Building a rigid structure across an active seismic boundary like this is an extraordinary engineering challenge. Modern bridges are actually built to tolerate a fair amount of ground movement, but a fixed structure spanning two independently shifting tectonic plates would still face serious risk during a major quake. A rigid underground tunnel would face similar problems, though it's worth noting that modern tunnels are typically built with bulkheads, emergency doors, and other systems designed to contain flooding rather than fail catastrophically all at once. The short, direct 14-kilometer route, sitting close to both the trench and the fault line, turned out to be far riskier than early planners had assumed. That pushed engineers toward a very different solution. Instead of taking the shortest path, they'd need to go around it. In 2005, a series of survey expeditions set out to map an alternative route, this time heading west into the Atlantic rather than following the shortest crossing point. Methodically scanning the seafloor, researchers identified a promising feature known as the Camarinal Sill, a natural underwater ridge offering a viable, if longer, crossing. This western route is roughly twice the length of the direct crossing, at about 28 kilometers instead of 14. When officials announced the longer route and the resulting delays to the project's timeline, the news drew criticism from people who felt it signaled the project would never actually be built. But the longer route offered real advantages. Depth data showed that along this path, the strait is only about 300 meters deep in most places, and the seabed here consists largely of soft clay and sand rather than hard rock. A bridge still wasn't practical on this soft ground, since heavy pillars would risk sinking into the sediment, so both countries settled on a tunnel instead. Soft clay and sand are easier to bore through than hard rock, and sediments like these can help dampen certain seismic waves during an earthquake. That said, this isn't a simple guarantee of safety. Soft ground can also amplify shaking in some conditions and carries a risk of liquefaction. So any tunnel built through it would still need to be carefully engineered with seismic risk in mind, not just protected by the ground itself. In 2023, Spain and Morocco reaffirmed their cooperation on the project and committed to renewed feasibility studies. The current concept involves 3 parallel tunnels. 2 for high-speed trains, designed to run at speeds over 200 km/h, and a central tunnel for maintenance, ventilation, and emergency evacuation. This long, difficult history spanning drained sea proposals, floating cities, deep trenches, and active fault lines reflects a broader lesson. Ambitious infrastructure has to work with a region's geology, not against it. Engineers didn't succeed at Gibraltar by forcing the shortest, most obvious path. They succeeded by rerouting around the strait's most dangerous features. Estimates suggest the first trains could potentially cross by 2040, though that date remains a projection rather than a confirmed completion date.